Good evening, everyone. I am Harshit Agrawal. Welcome to the 8th live session of mine for the week 8 of the course Structural Dynamics CE07. So, in today's session, we will cover following things. First, we will review what was covered last week. First, we will review what was covered last week, that is in week 7 of this course. Then, we will see what was taught in week 8, a brief overview just to brush up the content and get everyone on the same level, followed by recap and review. Today, we will see only one question, but in this single question, we will cover everything from scratch such that understanding this complete question will provide you thorough clarity to the past 2 3 weeks of content. And in this question, along with some manual calculation, we will mostly use MATLAB code, a very elaborative one this time. So, just like in the past live sessions of mine, I will step by step guide you how to code in MATLAB and we will see the results. So, if you have access to MATLAB, just keep it open in your laptop or PC. Else, just write syntax along with me and try to replicate it later on. And if any doubts, can ask me in the next live session. Okay, so I hope everyone are clear with the instructions. If you have any doubt, If you have any doubt, can raise hands or write query in the chat box and I will respond as soon as I will see. Okay, so let's start. So during the week 7 of the course Structural Dynamics, we talked about multi-degree of freedom system. That is how a complex structure can be simplified into concentrated masses as a multi-degree of freedom system. Here we saw how dynamic equilibrium equation is written for a multi-degree of freedom system, how natural frequency and deformation profiles are obtained using eigenvalue and eigenvector solution of a determinant equation. We also saw some approximate methods for finding natural frequency for first mode of vibration. Now, what's the need of these? Usually, first mode carries the maximum mass participation. So, if we know the first mode without going through the tedious calculation of matrix solution, it will be a simpler solution. Now, so there are two methods in this. First is Rayleigh's method, which is based on energy conservation. That is, total energy is the sum of kinetic energy and potential energy. And when the total energy is maximum, either kinetic energy is maximum or potential energy is maximum. Now, since the maximum total energy will be the same, so the maximum kinetic energy will be equal to the maximum potential energy. And based on this logic or this concept, we deduced a equation for determining the natural frequency as shown on the screen. And this method provides the upper bound of frequency. So this method we also saw, and for this method we also saw a MATLAB tutorial wherein we discovered that as we get closer to the actual model shape assumption, our natural frequency value also converges to the actual one, but it is still greater than the actual one, and that's why we say Rayleigh's method provide the upper bound value of frequency. And second is the Dunkerley's method, which is based on the concept of flexibility coefficient, in which omega square is determined by the following equation as shown on the screen, and the flexibility coefficient is just the inverse of stiffness coefficient. And this method provides the lower bound value of frequency. We saw one numerical in which we calculated both frequency using Rayleigh's method and Dunkerley's method, and we saw it was giving a bound to the actual frequency that we obtained from matrix solution. Okay, so this was what we learned in the last week, that is in week 7. Now, in the week 8, we learned about time history analysis and response spectrum analysis, in which we learned how a complex building can be converted into a multi-degree of freedom system, and thus how deformation of each floor can be obtained thereafter for a given or a known earthquake ground vibration. The content of week 8 is divided into different modules as in week 8 module 1 we read about time history analysis, how to write dynamic equilibrium equation in matrix form, and then how to simplify it for a known ground acceleration, and how participation factors comes into action. And in week 8 module 2 we learned about response spectrum analysis, how spectral deformation profile can be clubbed into dynamic equilibrium equation in matrix form, and how maximum deformation of each floor can be obtained. So moving ahead, we'll just brush up all the formulae and relations we saw last week, this week, so that everyone can understand the numerical and the MATLAB part coming ahead properly. So just to brush up things, the dynamic equilibrium equation is given as inertia force plus damping force plus stiffness force is equal to externally applied force. Assuming that a frame is rigid and deflection can happen only in horizontal direction and mass of the supporting column is negligible, the actual frame structure can be transformed into an analytical model as shown in the figure. Now, this is something that we have been reading since week 1 of this course. Till week 6, all the discussion were for single degree of freedom system, but in reality, a structure is a complex system which can be seen more accurately as a multi degree of freedom system since it generally rises up to multiple floors and thus can't be concentrated at a single point. Thus, an actual complex structure is broken down into multi-degree of freedom system in which number of floors is equal to number of degree of freedom, and thus this structure with concentrated mass of each floor and known stiffness of columns, assuming no lateral deformation or buckling, can be simplified into a spring block system as shown in the figure in the right. And thus for these systems the dynamic equilibrium is written in matrix forms as mu double dot plus cu dot plus ku is equal to p, where m is the mass matrix, c is the damping coefficient matrix, and k is the stiffness matrix. Now things to observe in these mass, damping, and stiffness matrix are all the three are symmetric matrix, they are positive definite, and they are coupled. So these equations, suppose we have a three-story building, then we have three unknowns, the deformation of all the three floors. Now these three equations can be solved independently. Why? Because the stiffness matrix and the damping matrix are coupled matrix, so equations can be solved independently. However, deformation now will change not only with time but with also with position of mass, that is first floor, second floor, and so on. Thus, deformation can be written as a function of both time and distance as phi of t and as a product of phi of t and q of x. Now, since x will have different distinct known values, those are floor heights. Thus, velocity and acceleration can be deduced as u dot is equal to q dot into phi, and u double dot is equal to q double dot into phi. Now, since phi is a modal matrix, we saw last week about orthogonality of modal matrices and the property of decoupling associated with them. So these coupled matrices of K, C, and M can be decoupled using phi to obtain resulting matrix as diagonal matrix. Now, once the decoupling is done, the dynamic equilibrium equation can be simplified as follows, substituting C by M by 2 epsilon omega and K by M by omega square. Now, thing to observe here is the new factor Pi, which is nothing but participation factor of a particular mode of vibration in total vibration. And why this is important? Because not all mode contributes equally in total vibration of a structure. Most often mode 1 contributes the maximum compared to other modes. So it is important to know participation of each mode to obtain accurate deformation of each floor. Now, how this is taken into account? There are two methods. First is time history analysis. In this method, we know the ground acceleration. So, step 1 will be to find the modal frequency and modal deformation for each floor, and step 2 will be to find the total deformation of a particular floor as the sum of deformation at that floor due to different modes of vibration. Now, suppose there are large number of vibration modes. So, how many modes we need to consider? We need to consider only those modes where mass participation is greater than 95%. So, suppose there are 10 floors, so we will have 10 modes, 10 deformation, 10 modes of vibration. Suppose the sum of participation factor of first four modes is becoming greater than 95%. So, we need to consider only those four modes and we need to leave ahead the rest six modes. So, this is how we consider vibration modes when there are large degree of freedom. And second is response spectrum analysis. In this, acceleration spectrum is known. So, and second is response spectrum analysis. In this, the ground acceleration spectrum is known to us. So, step 1 will be for a particular system, we can obtain the deformation spectrum, the spectral deformation. And since this spectral deformation is a function of omega and epsilon, however, all modes of vibration don't participate equally. So, the deformation of a particular floor and in a particular mode will be maximum. The maximum deformation of a particular floor and at a particular mode will be given by a product of participation factor into modal vibration into spectral deformation value. However, the maximum value for a particular floor won't occur at the same time for different modes of vibration. Thus, they can't be added directly. Hence, we use square root sum of square method technique to add the Qmax as given below. So I hope the weak content is clear to everyone. So now we'll proceed on with the questions. So this is question number 1. The structure to be analyzed is a three-story steel rigid frame as shown in figure. The structure is subjected to El Centro's earthquake. The weights of the floor are indicated in the figure. Assume the width and the depth of the column be 40 centimeter and 15 centimeter respectively. The weight of the column be 20 kilonewton per meter. Determine the response spectrum for deformation, velocity and acceleration using Newmark's beta method, and the natural frequencies corresponding modal shapes of vibration, and maximum deformation of each floor using response spectrum analysis. So I will give you a couple of minutes to think about the question and then we will see the solution. Okay, so let's see the solution now. So we have been given a three-story building. Am I audible? Yeah. So we have been given a three-story steel rigid frame, and the structure is subject to El Centro's earthquake. Now I have the database for El Centro's earthquake, and it looks like this. So this is the time and the ground acceleration value. It ranges up to 30 seconds, 31.18 second, and this is how the vibration of ground is occurring. This database is freely available online, so I have picked the database from any source, and this is the El Centro's earthquake vibration. Okay, so the structure is subjected to El Centro earthquake. We know the weight of the floors and the columns, and we need to determine first the response spectrum, then natural frequency and modal shape, and maximum deformation. So what will be the steps to solve this question? First, we'll form the spectrum deformation profile. How? Using Newmark's beta method. This we saw couple of weeks back, but in that question we saw for a constant ground acceleration. This time it is continuously changing ground acceleration. So first is this. Second step is to obtain mass and stiffness matrices. Third step is to calculate the eigenvalues and eigenvector. Once we know the eigenvalues, we need to obtain periods of vibration. Now we know the periods of vibration and we know the spectral deformation profile. So from SD curve, we will get SD values for respective periods of vibration. And once we know the SD values, we will calculate participation factors for each mode of vibration, and at last we'll calculate maximum deformation of each floor using response spectrum analysis via SRSS method. I hope the steps are clear to everyone. So let's look ahead now. So first step is to obtain the spectrum responses. So now I will be opening my MATLAB software in my laptop. You can see how to code as of now and implement the same later on. We will go step by step and define everything properly and clearly. So this will be a slightly bigger MATLAB code, so I will request everyone to please be patient or and pay attention to understand everything. All the syntaxes that I will use today are a little complex than the last time, so please pay attention. I will try to clarify all of them with time, but try to learn more about them from MATLAB official webpage. And the more you will practice, the more clarity and command you will gain on these things. So let's start. Okay, first I will clear my screen. Okay, so first step is to import the El Centro's earthquake database. So this is the file that I have stored in my MATLAB software in my MATLAB folder. So you can double click the file and you can see this is the database of El Centro's earthquake. There are 1560 points. Okay, so you just need to convert the output type into numeric matrix and select the import option. So okay, so once it is done, you can see in the workspace our database has been uploaded. So first step is to define the given values. So what are the given values? From El Centro's earthquake, we will take the time values. So El Centro data. So we saw in the Excel file, the first column is time and the second column is the ground acceleration. So again, going to our database. So the first will be time. So you can see in the workspace the uh, main database will get broken, and second is the ground acceleration. Okay. After this, we will define the acceleration due to gravity value, which is 9.8, and we define the delta t value. Delta t value will be nothing but difference between two consecutive points in the time matrices that we have obtained. And let's define mass of the system to be unity, since we are forming the response spectrum, and the initial period of vibration, let's take it as 0, since we need to obtain the response spectrum, which is nothing but the maximum deformation or maximum response with respect to time period. Okay, and let's define a variable tt, which is nothing but length of t, which will help us in creating loops. And since damping is not given, so we'll define xi is equal to 0. Why we are defining xi here? So that later on, if the damping is considered, so we can just append the code by an xi value and we don't need to make any changes later on. Okay, and we will define an endpoint. What is endpoint? Till what time period we want to observe. So let's say we want to observe till 25 seconds. So let's define endpoint as 25 seconds. Okay, so now we will go on with the estimation. So these are all the given values that we wanted to define. In estimation, there will be two loops. First loop will change the time period, and the second loop will change the time within that time period, so that we can obtain the maximum response for a particular time period. Okay, the same thing we saw a couple of weeks back also. So I hope you remember those concepts. If not, you can see that problem once, because it was a simpler for problem than this, and the same we are doing today again. So first loop is for j equal to 1 to round endpoint divided by dt. So this will help us to create different points for time period. First step will be to define omega for each time period. So omega j comma 1 will be nothing but 2 pi by tj. A will be stiffness will be omega j square times m, and damping coefficient will be 2m omega j times xi. The damping coefficient will be 0 in our case, but I am defining so that later on, if you are again using the code but with some damping, so you can be clear how to take damping into consideration at that time. Okay, so these are the basic system parameters for a particular time period. Once recheck whether we have defined everything properly. Okay, we are good to go ahead. Now we need to apply the Newmark's beta method. So linear acceleration method, which is nothing but Newmark's beta method. In this, gamma is taken as 1 by 2 and beta is taken as 1 by 6. This is predefined values. Now, what are the initial condition? Let's assume initially the system is at rest. So u1 will be 0, v of 1 will be 0, and a1 will be 0. So in Newmark's meta method, we need to define a bar, a, and b. There are three constants that we need to define that will help us in the function later on. These all things we have discussed in the past, so I am directly writing the code for them. So k bar is nothing plus but k plus gamma c upon beta delta t plus m upon beta delta t square. So k plus gamma c divided by beta delta t plus m upon beta dt into dt. So this is a bar. A will be nothing but m upon beta delta t plus gamma c upon beta. M upon beta delta t plus gamma c upon beta. And b is nothing but m upon 2 beta plus delta t c whole into gamma upon 2 beta minus 1. So m upon 2 beta plus delta t into c into 0.5 gamma upon beta minus 1. So these are k bar, a, and b values. Now once we have defined this for the function, we need to define the initial condition. So u naught will be u, v naught will be v, a naught will be a. Now these were the parameters that we need to define for Newmark's beta method. Now we need to again initiate a loop within the first loop that will be for each time step. So loop over each time step. So for I is equal to 1 to last point, that is tt minus 1, df will be nothing but my the linear change in acceleration force. So that will be given by minus g dot star agi plus 1 minus agi. Now we need to call the Newmark's function. So this function we defined earlier also. So I will just won't write the function again, but I will just show you what the function is. So this is how we define a function. These are the input output that we'll get from the function, and this is the inputs that we'll give to function. The function name is newmark. So in this, first we have defined the df bar, how df bar will be obtained from the values that we are given, then how delta u will be obtained, delta u dot will be obtained, and delta u dot dot will be obtained. These are formulas we have discussed in the content before also. Once we know the value of delta u dot, and delta u dot dot, the before the responses ahead can be written as u is equal to u naught plus delta u, v is equal to v naught plus delta u dot, a is equal to a naught plus delta u dot dot. U naught, a naught, v naught we have given in the input, that is nothing but the initial parameters, and then time will be appended. Once this loop will end, the u naught v naught value now will change to u v and a, the time will be appended, and again the further u, v, and a values will be obtained. So this is how this function will run over a loop for time tt minus 1. So tt is the total length, that is 1560 points. So for 1559 points, this is how the function will run. We'll obtain the u, v, and a value for each time step, and then later on we will get the maximum responses value, that will be for a particular time period. Then for changing time period, again this function will run, and thus we will obtain a spectral deformation profile. So here we will call the Newmark's function t comma u comma v comma a. These are the responses that we want, is equal to Newmark t comma a comma b comma df comma dt comma k bar comma u naught v naught a naught gamma beta. So these are the inputs, and this is the output. Once we have obtained the output, we need to store the output in a matrix. So u comma I will be nothing but the value of u that we have obtained from there. Similarly, v of t1 will be nothing but the value of v that we have obtained from the function above, and a of t1 will be nothing but the value of a that we have obtained from the function above. Once this is done, we need to again set up initial values for next loop within the same time period. So how it will be done? U naught will be changed to u, v naught will be changed to v, a naught will be changed to a, and t will be t only, since t is appended earlier. So this is how this inner loop will end. Now once this loop ends, this is for a particular time period. We have obtained the deformation at each time interval for a particular time period. So next step is to estimate the maximum values at the given period. So it will be done. U max will be nothing but absolute maximum of absolute of u of t1. V max will be nothing but maximum of absolute of v of t1, and A max will be nothing but maximum of absolute of A of t1. So this is how we'll obtain the maximum responses for a particular time period. Now we need to form the spectral deformation profile. Now once we have obtained the maximum deformation value, the next step is to estimate the response spectrum for deformation, velocity, and acceleration. So how this will be done? We'll store it in matrices. So sdj comma 1, j is the initial parameter that we will running for time period. So sdj comma 1 will be nothing but umax, spv, that is spectral velocity, j comma 1 will be nothing but sdj times omega j. This relation we have seen earlier also. And spa, acceleration, j comma 1 will be nothing but sdj times omega j, omega j square divided by g into g. These all relationships has we have seen. And t j plus 1 comma 1 will be nothing but tj plus dt. Okay, now we will end the second loop. So if there are no errors in both the loops, then our function will run successfully and all the parameters will get defined here. So you can see our function didn't give any error, so it means that the function has run successfully, and we have, you can see here all the parameters have been defined properly. Now we need to read these parameters. So first we'll define some boundary conditions. sb1 comma 2 comma 1 will be 0, spv 1 to 2 comma 1 initially boundary conditions, these are the zero values. And spa 1 to 2 comma 1 will be maximum of absolute of ag divided by g into g. Okay, and ag and we will define as the blank matrix, and t and will define as blank matrix. So these are just some boundary expressions that we need to define, and frequency will be nothing but 1 upon t. Okay, so now we'll form the figure. So let's call figure function. In the figure functions, this, since we need to form spectral profiles for acceleration, velocity, and deformation, we'll use this subplot function. So subplot 3 comma 1 comma 1. So we are dividing a single plot into 3 rows. First will be for acceleration, second will be for velocity, and third will be for deformation. So in the first row, let's define, let's plot spectral acceleration. So title will be spectral acceleration. X label will be period in seconds, and Y label will be SA. Similarly, subplot 3 comma 1 comma 2, this will be for velocity. Title will be spectrum velocity. X label period, and Y label And finally subplot 3 comma 1 comma 3. So in this plot 3 comma spectral displacement, title will be information, X label again period, and Y label is B. Okay, so let's see the graph. So this is the response. So you can see this is the spectral acceleration response, this is the velocity response, and this is the deformation response. Now what we'll do, we will first calculate the eigenvalue and the eigenmatrices. From eigenvalue, we'll get the period of vibration. From the known period of vibration, we will estimate the spectral deformation values, and then we will find the maximum responses. Okay, so this is how we obtain the spectral acceleration, spectral velocity, and spectral deformation. Okay. So before moving on to the next step of the code, we first need to form the mass and the stiffness matrices. So second step is defining system parameters again. So since the building is modeled as a shear building and under the assumptions stated, the entire building may be represented by the spring mass system as discussed earlier. The concentrated weights which are each taken at the total floor, each taken as the total floor weight plus the that of half of the column above and half of the column below are computed as follows. So w1 will be nothing but the weight of the first floor and half of the weight of the columns above and half of the weight of the columns below. So you can see here in the question it will be 60 into 30 plus 2 into 10 into 20 plus 2 into 5 into 20. So 60 into 30 plus 2 into 10 into 20 plus 2 into 5 into 20. So this is weight. So mass will be nothing but 2400 upon 10. I have taken 10 so that it can simplify the calculation ahead. Okay. Similarly, weight of second floor will be 30 into 30 plus 2 into 5 into 20 plus 2 into 5 into 20. So 30 into 30 plus 4 into 5 into 20, which is 1300 kilonewton, and thus m2 will be 1.3 into 10 to the power 5 kg. And finally, weight of third floor will be 15 into 30 plus 2 into 5 into 20. So 15 into 30 plus 2 into 5 into 20, which will be 650 kilonewton, and thus M3 will be 0.65 into 10 to the power 5 kg. Okay. So once we have obtained the mass, then the next step is to determine the stiffness. So equivalent stiffness will be nothing but, since the columns are in parallel, so the equivalent stiffness we discussed in the week 1 of the course is given by 2 times the stiffness of one column. So K1 will be 2 into 12 EI by L cube. We know E, which is nothing but 200 GPa for steel. So it is 200 into 10 to the power 3 MPa, and I is BD cube by 12. So the width and the depth of the column was given 40 centimeter and 15 centimeter, and we know the length, the height of the column. So for first floor it was 20, then 10, then 10. So K1 will come out to be 67.5 Newton per mm, K2 will be 540 Newton per mm, and K3 again will be 540 Newton per mm. Okay. So once we have defined mass and the stiffness matrix, the mass matrix will be given by this, and the stiffness matrix will be given by this. The equations of both the matrices we know previously. And once this is defined, we can write the characteristic equation K minus delta M is equal to 0. Determinant of K minus delta M is equal to 0. K minus lambda M. Lambda is nothing but omega square. And thus this equation will be written like this. Now we will write the same equation in the MATLAB and we will calculate the eigenvalue and eigenvector and eigenvalue from the inbuilt MATLAB eigenfunction. Okay, so let's move on to the code ahead. So next step will be first define mass matrix. So I will define mass matrix. We know space means same row and with the semicolon we are changing the row. So it is 2.4 into 10 to the power 5, so 2, 4 and 4 times 0, space 0, space 0. Now we need to change row. So it will be 0 space 1.3 into 10 to the power 5, space 0. Then again semicolon 0, 0, 0.65 into 10 to the power 5. Okay, so this is the mass matrix. I am printing the matrix also so that you can see whether it is defined properly or not. Now we need to define stiffness matrix. Stiffness matrix capital K is given by we saw 6.075 into 10 to the power 5. So 607,500 space minus 5.4 into 10 to the power 5, 54, 4 times 0, space 0 semicolon minus 5.4 into 10 to the power 5, 2 into 5.4 into 10 to the 108, 10.8, 2, 3, 9, minus 5.4 into 10 to the power 5, semicolon 0, minus 5.4 into 10 to the power 5, 5.4 into 10 to the power 5. So this is stiffness matrix. Now we need to solve for eigenvalue and eigenmatrices. So solve for eigenvalues that will define by D and eigenvector that will define by say A. So A comma D will be given by eigenfunction EIG will take K stiffness matrix and comma M mass matrix. So how this function will read, A is the eigenvector. So it will be a 3 cross 3 matrices. So you can see A is a 3 cross 3 matrix and D is again a 3 cross 3 matrix in which the diagonal elements will be the eigenvectors, eigenvalue. Okay. So if we want to obtain omega and we want to see the order, so we'll define omega comma k. So we need to sort. It is unsorted. D is unsorted. If we don't know the sequence, what is the first mode of vibration, what is, so it is nothing but we will just take the diagonal element of D, we'll square root them so that we obtain omega and we will sort it. So these are the omega value 0.3883, 2.1008, 3.8187, and this is this omega is first mode of vibration. This is for second mode of vibration. This is for third mode of vibration. Alternatively, we can define natural frequencies like omega is directly equal to square root of d, just to simplify things. Okay. Once we define natural frequency, the time periods and be obtained as t is equal to 2 pi dot star omegas. So these are the time period: 16.1794, 2.9909, 1.6454. Okay. Now we need to obtain the eigen values, assuming that the deformation of top floor is unity with respect to top floor. So changing top floor deformation to unity and calculating deformation of remaining floor. How we will do this? First, let's take the eigen matrix, the A vector. So this will be for first mode of vibration, A2 will be for the deformation for second mode of vibration, and A3 will be for third mode of vibration. Okay, once we know these value, let's set A31, that is deformation of third floor in first mode of vibration, to unity. So A21 will be nothing but A1 of 2 comma 1 dot star dot divide A1 of 3 comma 1, and A11 will be nothing but A1 of 1 comma 1 dot divide A1 of 3 comma 1. I hope you are understanding how we are writing this equation. You just need to imagine what this A1, A2 and A3 means, and thus you can see how we are calculating A11, A21 and A31. Okay, this is done for first mode of vibration. Now A32 we will set as 1. So A22 will be nothing but A2 of 2 comma 1 dot divide A2 of 3 comma 1, and A12 will be nothing but A2 of 1 comma 1 dot divide A2 of 3 comma 1. Similarly, we will write the expression for third mode of vibration, which is A33, again we'll assume as 1. So A23 will be given by A3 of 2 comma 1 dot divide A3 of 3 comma 1, and A13 will be given by A3 of 1 comma 1 dot divide A3 of 3 comma 1. Once this is done, we'll define a blank matrix A. We'll store all these values again. So A dot star 1 is nothing but A11, A21, A31, A dot say for second mode of vibration it is A12, A22, A32, and A dot comma is nothing but A13, A23, A33. Now we can print this matrix, so you can see this is the deformation for first mode of vibration. This is for floor 1, floor 2 and floor 3. Again for second mode of vibration, floor 1, floor 2 and floor 3, floor 1, floor 2 and floor 3 for third mode of vibration. So how this is looking? This is looking like this. So we wrote this equation, we solved, so we got natural frequencies like this. Then we calculated deformation for each mode of vibration. So this was for first mode, this was for second mode, and this was for third mode of vibration. Accordingly, for first mode of vibration, the profile will look like this. For second mode of vibration, it will cross the y-axis by at one point, that should be done. And for third mode of vibration, the profile will look like this. So these are the deformation profile for each mode of vibration. Now we need to calculate the maximum deformation of each floor using response spectrum analysis. So how to do that? From known time periods and SD curve, let's first obtain SD values for all three modes of vibrations. Okay, so first will be for T is equal to 16.1794. 16.1794. So I will define SD1 is equal to, now we'll need to use the curve. So here we will get close to the exact value. So this seems to be very close. So this point is SD1 will is nothing but 0.841409. 0.841409. So this is SD1. Second is for T is equal to 2.9909. For T is equal to 2.9909. So SD2 will be given by 2.9909. So this seems to be very close to the exact value. So it will be 0.581226. 0.581226. Okay, so this is SD2. Now third step is for T is equal to 0.1654. 1.6454. So SD3 is nothing but, okay, so this seems to be very close. 0.244221. 0.244221. So this is how we have defined all the SD values. Now next step is calculating participation factor of each mode of vibration. So how this is done? We first need to define the multiplying matrix, the constant matrix. What is this constant matrix? The uh, this matrix one. Since it's a three-story building, so it will be a identity matrix of 3 cross 3. So we can define it is a 3 cross 1 matrix of 1 unit. So since this is 1 cross 3, this is 3 cross 3, so multiply it will become 1 cross 3, then this should be 3 cross 1 matrix. So it will, I will define it as Cm is equal to 1 comma 1 comma 1 colon 1 1 colon 1 semicolon 1 comma semicolon semi 1. So participation factor P1 will be given by A1 transpose times M times Cm divided by A1 transpose times M times A1. A2 again will be the same thing, just the deformation matrix will change. And P3 again for third mode of vibration. Now the total participation factor should be equal to 1. So let's check P1 plus P2 plus P3. Since it is 1, this means that the calculation is correct. Now the final step, estimation of maximum deformation using response spectrum analysis. Okay, so for first floor it will be given by u1 is equal to square root of P1 into first floor deformation into SD square plus P2 second floor deformation SD2 square plus P3 third floor deformation SD3 square. So it is nothing but P1 into A11 into SD1 square plus P2 into A21 A12 times SD2 square plus P3 times A13 times SD3 square. Similarly, U2 will be square root of A1 times A21 times SD1 square plus P2 times A22 times SDP2 square plus P3 times A23 times SD3 square, and U3 will be SQRT P1 times A31 times SD1 square plus A2 times A32 times SD2 square plus A3 times A23 times SD3 square. So these are U1, U2 and U3. So you can see in the workspace, or I can print also. U1 is this, U2 is this, and U3 is this. So these are the deformation values. So we got U1, U2 and U3 as 0.8171, 8171, U2 as 0.8644, and U3 is 0.8808. Okay, so these are the maximum deformation of each floor using a response spectrum analysis. So this was all to solve in the question, and this is the code layout for your reference later.